Hello, my name is Madhav Raj, and I'll be presenting our work on human perception and machine recognition of speech, a case study with respect to unvoiced segments and gender of the speaker. This will be the overview of my talk. The speaker's gender does not strongly influence the acoustics of unvoiced sounds as they do for the voiced sounds. In this study, we established this hypothesis by conducting both objective and subjective experiments. We prepare the speech corpus by replacing the unvoiced segments of the utterances by corresponding unvoiced speakers of a speaker of opposite gender. We do both objective and subjective evaluations. In objective tests, we build phoneme recognition models and test those models with these modified utterances. For subjective evaluation, we ask human subjects to listen to the modified and the original utterances and to distinguish them. The phoneme error rates from the objective evaluation and the listening test scores from subjective evaluation are presented, and we show that the speaker's gender influences acoustics of voiced sounds strongly than they do for unvoiced sounds. We have used timid database for all our experiments, and in this timid database, the speech files are annotated at phone level, and we have used a particular set of utterances named SX in timid database for our subjective evaluation experiments. And to replace the voice segments and unvoiced segments of uh, any audio file, it is not a straightforward process, even though the utterances are same. So we have used dynamic time warping algorithm to do that. And for listening tests, we have taken a total of 25 audio stimuli and presented to total 50 subjects. Out of these 25 stimulus can come from any of the six categories as follows. That is the original utterances spoken by male speaker, original utterance spoken by female speaker, and the modified utterance, that is a mixed signal where uh, the unvoiced where all the unvoiced segments and two consecutive voice segments of male speaker are replaced by the corresponding segments of female speaker and vice versa. And the next category of signal is a mixed signal where only the unvoiced segments of male speaker are replaced by the corresponding segments of female speaker and vice versa. For objective evaluation, we have built phoneme recognition systems with Caldi toolkit, and we have built these four types of acoustic models. One is monophone model, the next is context dependent triphone model, next is LD and MLLT model, and next is speaker adaptive model. So each of these models are trained separately for male speech and female speech, and these trained models are tested on mixed speech signals. So this is the algorithm for generating the stimuli, that is to mix source and target signal. So to mix uh, the voiced and unvoiced segments of same utterances spoken by two different speakers, we use this algorithm called dynamic time warping to align the utterances. Even though the two utterances may be the same, but they might have phonetic transcriptions, they might differ, and so the number of phones might also differ. So to effectively handle these variations, we first map the phone transcriptions of the utterances to either unvoiced or voiced and use DTW to align the transitions between voiced and unvoiced and unvoiced to voiced. So we then construct a mapping table based on the optimal path obtained after DTW's backtracking algorithm. And using this mapping table, we pick the voice segment from source and unvoiced segments from the target waveform and stitch them together and mix the signals. After mixing, we perform low pass filtering at all points of stitching to avoid discontinuities in the signal. So this is the algorithm for as a flowchart to illustrate the mixing procedure. First, we take the source waveform with its alignment, map the phones as either voiced or unvoiced, get the transitions, and we do that similarly for the target waveform. and perform backtracking and align the transitions, and then copy the voice segment from source and voice segment from target, and stitch them together and perform low pass filtering to get the mixed speech. And this is an example speech where the source is from male speaker and the target is from the female speaker, and we mix them where we copy only the unvoiced voiced portion from the source, and I mean unvoiced portion from the source and voiced unvoiced sounds from the female speaker are mixed uh, to this signal to get the mixed signal. And we carry out subjective listening tests by playing uh, a total of 25 randomly selected stimuli from the six categories of the signal, these six categories of the signal, uh, and the listeners were asked to decide if they can hear only one speaker or two speakers in each of the utterance. And the recognition scores are given in this table where people can identify that uh, there is only one speaker in the original um speech 98% of the time and 99% of the time for male and female speech. And when we mix uh, voiced two consecutive voiced and unvoiced signal, most of them were able to identify that there were two speakers. But if we mix only the unvoiced portion, uh, then none of them were able to identify. I mean, most of them were not able to identify that the mixing had happened. So, and for the objective evaluation, we have conducted, we have built gender-specific phoneme recognition models separately for male and female using timid utterances where uh, 3,200 sentences are male and 1,360 for female are used for training the gender-specific models. With flat start phone alignment, we iteratively build monophone model, context-dependent triphone model, and LDMLT triphone model, LDMLT speaker adapted triphone model. And we present the original and the modified utterances as test utterances for these trained gender-specific models, and we report the phoneme error rate. And these are the phoneme error rates where um, the source signal is the male speech signal, which is tested on both male trained model and female trained model. And this is where this is the original male utterance, and this is the male utterance where the unvoiced segment of another male speaker is mixed. Here, the stop and the silence portion of female is mixed to the source male speech, and here the female of unvoiced segments of female is mixed to the original male speech, and here two consecutive voice segments and all unvoiced segments of female are mixed to the male speech. And similarly for female uh, source signal. So from these tables, we see that the phoneme error rates are lowest when the original male utterances are tested on models trained only on utterances from male speaker. And similar trend is seen for female utterances tested on female speech as well. As we mix more and more segments, the phone error rate gradually increases for both male and female models. And the influence of gender on stop consonants is much more significant than that on fricatives. And the phone error rate increases even when the source and the target utterances are from the same gender but from different speakers. And conclusion, to understand the influence of speakers gender on unvoiced sounds, we have conducted both subjective and objective experiments. When the acoustic signals of the unvoiced segments are replaced by the corresponding segments of opposite gender, the listeners are unable to identify the change in speaker. However, based on the phoneme error rates of the phoneme recognition models, we see that the speaker's gender does influence the unvoiced sounds. Thus, based on these contradictory findings, we hypothesize these three things. One is the listener may use speaker independent acoustic cues to identify unvoiced sounds. And the second, listeners may not use unvoiced sounds to identify the gender of the speaker. And the third, listeners may not use speaker normalization techniques to identify unvoiced sounds. And finally, we propose that The speaker recognition systems must give higher weightage to models based on speech production mechanism, whereas to build speech recognition models, we must give higher weightage to models based on speech perception mechanism. And these are the references. Thank you.